In the current lecture, we will continue looking at an analysis of simple loop-like programs and their impact as far as the cache is concerned. Our interest is to try to understand how the cache hits or misses will be determined by the nature of the program, and what we can do to improve the cache behavior as far as the program is concerned. We are looking at simple examples to allow us to do a complete analysis. In the previous lecture, we had been looking at an operation on two-dimensional matrices. The operation was basically adding the elements of two-dimensional matrix term for term. I refer to this as two-dimensional matrix sum, and we had a loop which had a problem with it, in the sense that, if you refer back to the slide from the previous lecture, the loop was dealing with two matrices A and B, each of which was a two-dimensional matrix of 1024 rows, each of 1024 columns, and I was adding the element of A to the corresponding element of B and putting this as a new value of the element B by going through the matrices column by column. That is what the two for loops that we have used amount to, because of the way that the for loops are structured, it amounts to going through the matrices A and B column by column. But as we learned in the previous lecture, for a C program, one could safely assume that the elements of the matrices are stored in memory row by row, and therefore by accessing the elements of the matrix column by column in this program, I would not be benefiting well from spatial locality of reference. So the idea which we looked at last time was how one could just interchange the J loop and the I loop without changing the meaning of the program and get that benefit. For example, if I modify the program so that the I loop was the outer loop, so always the outer loop and the inner loop. So previously the J loop was on the outside, but I have now moved it on the inside, so the J loop is the inner loop. And we noticed that now the situation is that the reference sequence is that I load A of 0, 0. The first time through the loop we are dealing with I equal to 0 and j equal to 0. The second time through the loop we are dealing with I equal to 0 and j equal to 1, and so on. In other words, we are actually going through the matrices row by row. And in terms of the diagram which we had used in the previous class, I view the two-dimensional matrix as being rows. These are the rows and these are the columns of the two-dimensional matrix. And this particular program now is accessing matrix A by going through A of 0, 0 followed by A of 0, 1, which is the second element on the first row. So this program is now going through the matrices row by row, which is the same as the storage order and which would therefore benefit from spatial locality of reference. The same is true with the matrix B. Notice that B of 0, 0, and after that we access B of 0, 1. And this basically has to do with the way that the for loops are structured for this two-dimensional example. We notice that it is beneficial for us to have the index which is the inner loop as the second index of the matrices, in other words the column index of the matrices, and then we get this benefit of going through the matrices row by row. So that is something to look for in the programs as we write them. But towards the end of the previous class we asked this question. So you know that you want to get benefit of spatial locality of reference, but can you just arbitrarily interchange loops? Isn't that potentially going to change the meaning of the program? So let's look at an example where it is in fact going to change the meaning of the program. Here's a slightly more convoluted example. In this example, I am not dealing with two-dimensional matrices. I am only dealing with one two-dimensional matrix which is called A, but we are doing a more complicated operation on the matrix. So if you look at the way things are set up, I have the outer loop which is using index j. So once again we consistently talk about this as the outer and this as the inner. The outer loop is the one with the index j, and you will notice that the index j is the second subscript, is used for the second subscript of the matrix A in all the three places that matrix A is referred to inside the loop. Remember from our previous slide that what we want is that the inner loop index should be the column index, the column subscript for the matrices. But in this particular example, what we have is each time through the loop we are adding some element of A to some other element of A and making this the new element value of a third element of A. So the calculation is a little bit more complicated than the kind we've seen before. Let me just diagram what's happening here. The first time through this loop, we have j equal to 1 and I equal to 1, and therefore, what this is being calculated is a of I plus 1, which is going to be, remember that the first time through this loop I is equal to 1, I am sorry, j is equal to 1 and I is equal to 1. Therefore, a of I plus 1 is going to be a of I plus 1 j minus 1 is going to be a of 2 0, and a of I j minus 1 is going to be a of 1 0. Therefore, the first time through the loop we are adding a of 2 0 to a of 1 0 and making this a new value of a of 1 1. Similarly, the second time through the loop we are going to have j still equal to 1, but I equal to 2, because the second time through the loop the inner loop index changes to 2, and we therefore have a of 3 0 being added to a of 2 0, and this becomes a new value of a of 2 1, and so on. So, this is what happens across the iterations of this particular loop, doubly nested loop. Now, if you think about the calculation that is actually happening, you may ask, is this a meaningful kind of a calculation, or is this just a trivial example to show something wrong that will never occur in real life? Just remember how the modification to the matrix element a of ij is happening. So, basically the new value of a of ij is given by the old value of a of I plus 1 j minus 1. What is I plus 1? I plus 1 should be interpreted as, to find out the new value of the element in the ith row and the jth column, then you have to take the old value from the element in the I plus first row and j minus first column, and add to that the element from the ith row and the j minus first column. So, if I am concerned about how the element I j changes, I notice that I have to look at the element which is in the same row as it, but one column to the left, and add to that the element which is in the next row, but the previous column. And so, therefore, this diagrammatic illustration over here, it shows how a of ij is modified using the element to its left as well as the element which is below it and to its left. So, this is just another way of updating a matrix, and will have some relevance for different kinds of computations. It is not a trivial example, it is a systematic way to update a matrix along the lines of what we have seen over here. Now, unfortunately, with this particular doubly nested loop, we notice that we are not going to be able to benefit much from spatial locality of reference, in that this seems to be stepping through the matrix in the wrong order. And how are we getting some insight into what order will be beneficial? I am just using the observation from the previous example. You remember from the previous example, we came to the conclusion that it is beneficial in C programs to have things set up so that the index of the inner loop, in other words I, is used as the second subscript of the matrix. In other words, I do not want to see I as the first subscript, which is what is happening over here. I want to see I used in the second subscript, but unfortunately in this particular piece of code, j is the second subscript for all the references of the two-dimensional matrix A. Therefore, this is a situation where we would want to try to interchange the loops, make the j loop the inner loop and make the I loop the outer loop, which is what I will try to do. So, here I have arbitrarily just interchanged the loops. So, I have just done the interchange. I have taken the line which says for j and put it after the line which says for I. Now, if you actually step through the meaning of this modified program, which is what I have done over here. So, on the left we had what the program used to do, and over here we have what the program does now that I have done this loop interchange. You notice that it calculates in the first iteration a of 1 1, which is a of 2 0 plus a of 1 0. In the second iteration, remember that the inner loop index, which is now the j index, is going to change, and therefore, instead of modifying a of 2 1, we modify a of 1 2, and you will be able to do the calculation of what the indices are. You notice that it is a different calculation from what was happening in the case of the old loop, but that is okay as long as the net result on the matrix is the same. So, you could step through the entire set of the different operations and then look and see whether there is any reason to suspect that the net effect is going to be different from the net effect under the old version of the program. And the giveaway that something could be wrong would come if you look at the old version of the program, where in the code segment that I have over here, you will notice that in calculating the value of a of 1 2, the old value of a of 2 1 is used, but the old value of a of 2 1 is one which has already been computed in this loop, in the old version of the program. Whereas in the new version of the program, when I calculate the value of a of 1 2, I am not using a newly computed value of a of 2 1, but the original value of a of 2 1, which means that the meaning of the program is different. In other words, it is not safe to just interchange these loops by just moving the j loop header after the I loop header. The net effect would be to change the meaning of the program. The program does something different. Therefore, one would have to do this interchange of the loops a little bit more carefully. One cannot just move the loop headers and expect that the program will behave the same way. One has to properly understand what this program was doing. One wants to end up with a situation where the I loop is the outer loop and the j loop is the inner loop, but one may have to do something more fancy. For example, in this particular example, if you think about it for some time, you realize that one could correct for the problem with the meaning of the program by having the I loop modified so that rather than going from I equal to 1 up to 2047, it goes from 2047 down to the lower value. Now, this is a somewhat more complicated example, but I merely mention it to illustrate that there will be situations where loop interchange is not safe unless it is done carefully. But loop interchange will be beneficial from the perspective of improving locality of reference of a program. With this, we can look at a slightly more complicated example. We come to an example which many of you are familiar with, example which is matrix multiplication. So here we are talking about, I am going to be referring to two-dimensional matrix multiplication. So we have two, in the examples which I am going to use, we have two square matrices, and we multiply two square matrices to produce a product matrix which itself is a square matrix. And many of you will be familiar with the way that matrix multiplication could be done. In this particular piece of code, rather than telling you what the size of each matrix is, I am just using n as the size of the dimension. So n could be 2048, n could be 1024, whatever it is. So we have two n by n matrices, y and k, and what this loop is supposed to be doing is multiplying the matrix y by the matrix, the matrix y and the matrix z, multiplying the matrix y by the matrix z, and making this product, the product matrix is it's a value of the matrix x. So we are computing x equals y multiplied by n, where x, y and z are all two-dimensional matrices of size n by n, double. So over here we have a possible way to do this. In this particular piece of code, I am assuming that the double matrix x has been initialized to be all zeros. So x is initialized to be full of zeros, and the matrices y and z contain the values such that they are to be multiplied. So I have a triply nested loop, the I loop, the j loop and the k loop. Each time through the loop, we multiply a row of y by a column of z and make that the new value of, for example, in this particular piece of code, we multiply the ith row of y by the jth column of z, dot element by element, compute in fact the dot product, and make this a new value of the ijth element of x. This is one way to do the matrix multiplication for these two-dimensional matrices. So notice that I am doing plus equals and that I have initialized the matrix x to be zeros. This is a substantially more complicated example. So we need to try to understand this. It would be quite difficult for us to try to go through this by listing the complete reference sequence and trying to think of the base address of the different elements and computing what might be conflicting with something else. So it is fortunate that we have moved away from that mode of analysis to something at a slightly higher level. But just for a proper understanding of what's happening at a slightly higher level, let me rush through some parts of the reference sequence. So the way I had described it, you notice that the way that this implementation of matrix multiplication is working is that it multiplies the ith row of y by the jth column of z in order to compute the element for x of ij, and it does this by multiplying y of I 0 by k of 0 j, and then it multiplies y of I 1 by z of 1 j, and so on. So we could come up with a reference sequence, but may first observe that we are in a situation where first of all y of 0 0 is multiplied by z of 0 0, then y of 0 1 is multiplied by z of 0 1, y of 0 2 by z of 2 0, and ultimately that sum is what is put into x of 0 0. So, in this particular implementation, I am assuming that in implementing this addition, the compiler is not adding to the variable x each time through, but is actually accumulating this product inside a register and storing the value of the accumulated value into the element x only at the end of the iteration. So, there is only one reference to x each time in each of these lines, but there are n references to y and n references to z, and it is basically a multiplication of a row of y by a column of z to generate a single element of x. Now, if we look at how things are proceeding in this loop, for example, let me just look at x of I j. When I look at x of I j, I notice that there is the outermost loop. So, the I loop is the outermost loop, and the k loop is the innermost loop. We now have 3 loops, so I can't talk about outer and inner, I have to talk about outermost and innermost. But if I look at the reference through which x is referred to in this sequence, I notice that the column subscript is j and that the row subscript is I. The first subscript is I, the second subscript is j, but this is in keeping with our insight that we had derived from the previous examples, which is that we want the inner loop. So, between the I loop and the j loop, we notice that the j loop is inner to the I loop, the j loop is inner to the I loop, and it is the j loop, in other words the inner of the 2 loops, which is being used as the column subscript for x of I j. Therefore, in some sense I would be able to make the observation that as far as this program is concerned, it is referring to the x matrix row by row, which is what I am using in this notation. Similarly, if I look at the reference to the matrix y, I notice that the second subscript, the column subscript, is the k is coming from the k index, which is the innermost loop, which means that which is the desirable property that we had, which is leading me to believe that once again for the y loop, as far for this program, as far as the references to y are concerned, once again y is being referred to row by row. However, when I look at the z, reference to z, I notice that it has k as its first subscript and j as its second subscript, but k is the innermost of those two. Between j and k is the innermost loop, which means that this is a problematic reference in that it looks like the 2-dimensional matrix Z is being accessed column by column. And this being C code from the looks of it, we understand that the references to x and y will benefit from spatial locality of reference, but the references to Z will not benefit from spatial locality of reference, which is why in this reference sequence down below I have shown the references to x and y in green, sort of using green as a positive color, and I am showing the references to Z in red as a negative color, in that the references to Z are not going to benefit from the cache spatial locality of reference. Therefore, this is one way to set up matrix multiplication, but may not be the best way in terms of fully exploiting spatial locality of reference and temporal locality of reference for all the elements that are being accessed. Okay, now one comment which I would want to make at this point. If you look at the way that I was describing the way that this matrix multiplication function or this matrix multiplication nested loop is working, I described it as a situation where each time the objective was to calculate a particular element of x by multiplying. To calculate the I comma jth element of x, we multiply the ith row of y by the jth column of z, and in effect what we were doing was to compute the dot product of the ith row of y by the jth column of z. And in effect what the innermost loop was doing was computing that dot product. In the innermost loop we had k varying from 0 up to n, and y of I k was multiplied by z of k j, and this was accumulated. And if you look back at our discussion of the dot product, you will notice that this was in fact, this is the same as what we talked about then. So this implementation of matrix multiplication is actually using the innermost loop, where the innermost loop is computing a dot product. There are obviously other ways that matrix multiplication could be implemented, and let me just suggest that another possibility or another way to think about different ways that matrix multiplication could be implemented. One could actually think about interchanging these loops and thereby getting different versions of matrix multiplication rather than this dot product inner loop version of matrix multiplication. And you may want to think about whether it's fair to interchange the 3 loops arbitrarily. In other words, instead of having I followed by j followed by k loops, I could have k followed by j followed by the I loop. In other words, some arbitrary changing of the order in which the I, the j and the k loop were included. And as a simple example, just looking back, remember that I had the I loop outermost, the j loop intermediate, and the k loop as the innermost. What if I interchange the I loop and the k loop? And that's exactly what I've done here. I've left the content of the loop is exactly the same, x of I j plus equals y of I k multiplied by z of k j. But all that I've done is I've interchanged. The I loop used to be the outermost loop, the I loop is now the innermost loop. The k loop used to be the innermost loop, it is now the outermost loop. And it turns out that this too would be a correct implementation of matrix multiplication if this could be done appropriately. And the question is whether this would behave any better than the previous implementation of matrix multiplication. So we could run through the similar kind of analysis to what we did before. Remember that at this point the way that we're analyzing these versions of different implementations of matrix multiplication is by looking at the statement inside the loop, and for each term inside the statement we're trying to assess whether the matrix, the two-dimensional matrix which is being referred to there, is being referred to row by row or column by column. And assuming that this is C code, we would want the references to happen row by row. So we look at ij and we notice that the j subscript is outer to the I subscript, therefore this is not good. We look at y of I k and we notice that the k subscript is outer to the I subscript, and once again this is not good. We look at the z of k j and we notice that this is good because the second subscript, the j subscript, is inner more to the k subscript. So in some sense what we've done here is to create a situation where the reference to z is happening row by row. So all the references to the z matrix are happening in a row by row fashion, exploiting spatial locality of reference. But the price that we've paid is that the references to y and the references to the x matrix are happening column by column. The previous version where we had the dot matrix inner product, the dot product inner loop implementation of matrix multiplication, we had the references to x and y happening row by row, and the reference to z was column by column. In this implementation things have switched around completely. But note that there are other interchange reorderings of the three loops which might have different benefits, so you want to think about that to the extent that you have time. Okay, now one observation which I did want to make is for this particular implementation that we have on the screen right now, you will notice that as far as the inner loop is concerned, the inner loop is one where I varies from 0 through n, and therefore as far as the inner loop is concerned, z of kj is a constant. Z of kj is an element of the matrix z, and it doesn't depend on the innermost loop at all. Therefore for all of the n iterations of the innermost loop, the value of z of kj is the same. It is because the value of z of kj is determined by the value of k and the value of j. Therefore z of kj does not change within the inner loop, and hence can actually be loaded into a register once for each value of k and each value of j, reducing the number of memory references substantially. And therefore one should not really view z of kj as being a memory reference at all, since it is going to be loaded into a register, and within the innermost loop it will be accessed out of that register. And therefore thinking of the z references as being good because they are happening row by row, it turns out was of artificial benefit, because in reality one would not think of the references to z as being referenced out of memory, but rather as being maintained by the compiler, hopefully in a register. Therefore this in effect has to be viewed as being a very poor way to multiply matrices. Okay, now rather than looking at the different interchangings of the ordering of the I, j and the k loops of matrix multiplication, we'll try to understand how we can improve the quality of the matrix multiplication loop, a triply nested loop, by using some other techniques that we have seen. And one technique that we have seen some time back when we were talking about improving the quality of instruction sequences with static scheduling and so on was the idea of loop unrolling. You remember in loop unrolling we try to do more than one iteration of the loop each time through the actual loop itself by duplicating the code of the loop in order to do two iterations of the loop in each of the instances of the loop. So if I look back at my ijk, the original dot product inner loop version of matrix multiplication, this is the original version that we had. Let's try to think of this loop now from the perspective of loop unrolling. Let's see if we actually try to unroll one of these loops, what would happen. loop unrolling produced benefits when we are looking at instruction scheduling, it's conceivable that loop unrolling will either produce benefits or give us some insight into how to improve the quality of matrix multiplication, this matrix multiplication piece of code. So what shall I do in terms of unrolling? Let me start by trying to unroll the k loop. So what I'll do is, each time through the k loop, rather than computing just x of I j, I'll try to compute, rather than just computing one value of k, I'll try to do the computation for two values of k. So I'll do two iterations of the k loop in each pass through the k loop. And we know how to do that. That merely involves, each time through the k loop I increment k by 2, and then within the loop I compute not only y of I k multiplied by z of k j, but I also compute y of I k plus 1 multiplied by z of k plus 1 j. And I add both of these terms to y x of I j. So let me just go back. In the unrolled, before doing the loop unrolling, if I did one multiplication and addition each time through the loop. When I unroll the loop, I do two multiplications each time through the loop, and therefore I'm reducing the number of times that the k loop has to be executed. Okay, now the question which we need to ask at this point is, how does this impact the locality properties of the program? And you'll recall from the previous version of the program that we viewed the x of I j as being a good reference, the y of I k as being a good reference, and the z of k j was a bad reference. It was one which was the matrix k z was being accessed column by column, because the second subscript was outer more to the first subscript. Now, has this changed at all by unrolling the loop? If you look at the unrolled version of the loop, once again the x of I j is a good reference, y of I k is a good reference, y of I k plus 1 is still a good reference, because the column subscript is based on the k loop, which is an innermost loop. And once again the z references of z of k j and z k plus 1 j are both bad references. So that has not changed. In terms of coloring, I will say that this is good, this is good, this is good, this is bad, and this is bad. That has not changed. But what has changed? What has changed is that each time through this loop, I am referring to z of k j as well as z k plus 1 j. And what is the relationship between z of k j and z of k plus 1 j? Remember your picture of the matrix, two-dimensional matrix z. So here we are referring to k and j, and k plus 1 and j. So z of k j is one particular element of z, and z of k plus 1 j is the element in the next column. I'm sorry, in the same column but the next row. Therefore, we are not actually benefiting from the references to z of k j, z of k plus 1 j at the level of their second subscript is not good, but there is not even a situation where z of k j and z of k plus 1 j are in the same row. Therefore, we don't see any benefit from doing this. But that might just be because we have not done the unrolling that we should have done. So let's look at another possible mechanism for unrolling. For example, once again I go back to my original loop, but what I'll try to do now is I'll try to unroll two loops. I'll try to unroll both the j loop and the k loop. In other words, I'll try to do in each iteration of the k loop two multiplications, and in each iteration of the j loop I'll try to put the code for two values of j. Now, what will this amount to in terms of the code itself? You'll recall that the way that we handled the unrolling as far as the k loop was concerned was by incrementing k by 2, and then within the program body we did two iterations of whatever the k loop was supposed to do. We'll have to do something very similar over here. If I want to unroll both the j loop and the k loop, then I could start by unrolling. For example, we know that in order to unroll the k loop, what I had to do was to include two terms corresponding to two iterations of the k loop. What does it mean to unroll the j loop? It basically means that I need to do two iterations of the j loop, which will mean having the body of the loop occurring twice, one with the value j and one with the value j plus 1. Therefore, unrolling both the j loop and the k loop will make the body of the loop a little bit bigger. We now have two C statements each iteration of the k loop. Two statements are coming because I'm unrolling the j loop, and each of the statements has two terms in the sum because I'm unrolling the k loop, as in the previous example. At this point, Let me just clear the screen. Okay, so with the successful unrolling in both of these dimensions, this is what we have. And now let us look at what we have on the screen in terms of the locality of reference, spatial locality. Once again, we will observe that things have not changed if I look at each of these terms in isolation, because we have not changed the ordering of the loops, and we are basically not changing the order in which the subscripts are occurring in any one of these references. Therefore, there is no need to look at whether x of ij is good, whether z of kj is good or not. We know that all the references to x and all the references to y are happening row by row, and all the references to z are happening column by column. That could not have changed, because we have not changed the order of the loops, and we have not changed the order of the subscripts inside any of these array references. But what has changed? What has changed is that in the body of this loop, we now have instance of referring to z of kj as well as z of k plus 1j, but we had that in the previous unrolling that we tried. What's new is that we now have a reference to z of k j plus 1 as well as a reference to z of k plus 1 j plus 1. And what is the relationship between z of k j and z of k j plus 1? The answer, if you go back to your picture of the two-dimensional matrix Z, is that z of kj and z of kj plus 1 are consecutive elements in the same row of a matrix Z. So what we have in fact done by this more ambitious unrolling of both the J loop and the K loop is we have artificially created some spatial locality of reference. Why do I say that? I say that because even though the reference to z of kj might be a miss when this program executes, a little later in the same program there is going to be a reference to z of kj plus 1, and z of kj plus 1 is a neighbor of z of kj. In effect, what we have been able to do by doing this unrolling is to generate some spatial locality of reference. The spatial locality of reference as far as z of kj and z of kj plus 1 is concerned. There is a little bit more spatial locality of reference as far as z of k plus 1j, z of k plus 1 j plus 1 is concerned. And therefore, the unrolling has helped us by generating some spatial locality of reference and improving the hit ratio, because we are actually getting the spatial locality of reference from a program which until now was not showing spatial locality of reference to the references to the matrix Z. Recall, we were not concerned about the references to matrix X or Y. They were happening row by row, which is what we wanted them to be. But we have been able to do this purely through loop unrolling. So there is something in doing loop unrolling that we are going to get a benefit from the perspective of spatial locality of reference. Now what this could lead us to is a whole new perspective on how to set up matrix multiplication. Rather than trying to carry forward this idea of loop unrolling and increasing the amount of spatial locality of reference that might be available, we could try to distill out the essence of what is being achieved by this loop unrolling, and that is what I will henceforth call blocking or tiling. But let me just explain what I mean. Now, the idea of blocking or tiling is that we identified from our quick analysis of the matrix multiplication program, which had I, j and k, where I was the outermost loop and k was the innermost loop, that for the dot product inner loop version that we were dealing with, the references to the matrix Z were doomed in that they were happening column by column, and they had a problem with them. But what we saw was that by doing this unrolling of the loop J and the loop K a little bit, we were actually able to make use of elements of Z a little bit more. Like when the element of Z, JK was brought into the cache, we were able to use its neighbor, and that was happening entirely because of the unrolling. Therefore, if we carry this idea through and we say every time an element of Z is brought into the cache, we try to use all the neighbors of Z before they are eliminated from the cache by replacement, then this will provide a different perspective on how the matrix multiplication could be set up. Right? So the idea in general would be something like this. Again, I'm just going to try to illustrate it using a diagram. It may sound a little bit confusing, but will help us when we look at the code which is going to follow. So ultimately, I want to multiply a large matrix Y by a large matrix Z. We're assuming that they're square matrices. But the ideas that we're going to come up with will generalize to other matrices, arbitrary matrices as well. Now, let's suppose that I try to view what would happen if I broke each of the matrices up into 4 parts. So I just look at I divide each of the matrices into 4 equal parts. And I know that in order to multiply these two matrices and get the product matrix X, I could, instead of multiplying a full row of y by a full column of z to generate one element of x, I could do the multiplication in parts, as was happening in the case of the versions of matrix multiplication where I interchanged the loops. So if I number each of these parts as 0, 0, 0, 1, 1, 0 and 1, 1, and once again I am not talking about 0, 0 as one element of the matrix y, rather it is 1/4 of the matrix y, it is some collection of rows and columns. So 1/4 of the matrix of the matrix y is what I am referring to as y of 0, 0. Now in order to compute the product matrix x, I will have to multiply y of 0, 0 by y of 0 at z of 0, 0, and I will have to multiply y of 0, 0 by z of 0, 1. I will have to multiply y of 0, 0 by z of 1, 0, as well as y of 0, 0 by z of 1, 1. But instead of doing them one by one without regard to reusing the values, I will do it in a more calculated way. For example, I noticed that in order to generate the quarter of the matrix x, which I will call x of 0, 0, I really need to multiply y of 0, 0 by x of 0, or z of 0, 0, and y of 0, 1 by z of 1, 0. That is how I would calculate the matrix x upper quadrant. Right? So basically to generate the elements in the matrix x which are in that particular region of the matrix x, I need to do this multiplication as well as the other multiplication which I am showing over here, this multiplication. And that will amount to doing the multiplication of the rows of x y by the columns of z in order to generate the elements in this region of the matrix x. Now when I look at this subdivision of the work that has to be done to generate x of 0, 0 and expand it to the work that has to be done to generate x of 1, 0, in other words this quadrant of the matrix x, I notice that z of 0, 0 is reused and z of 1, 0 is reused, and therefore this gives me that clue as to how I could do the reuse of z. Once again, I am not concerned about the accesses to the matrix x or the matrix y, since they are happening row by row anyway, but I am gearing the computation to trying to reuse the elements of z. Whenever an element of z or a block of elements of z is brought into the cache, we want to do the other calculations which involve those elements of the matrix z. And that leads us to some calculation at a lower level to figure out exactly which elements have to be computed in order to get the benefit of the reuse of the elements of the matrix z. This could actually be encoded into what is called a blocked or tiled version of matrix multiplication. And this is the kind of implementation that one might find in a linear algebra package or elsewhere, or read about in a course on numerical analysis possibly. So the general idea now will be, rather than thinking about the matrix multiplication as I, j and k loop, we have to think of the matrix multiplication as happening at two levels. At the one level, we are thinking about multiplying blocks of y by blocks of z, and therefore I have a block index for y which is capital K and a block index for z which is capital J. And therefore at the highest level we think of the matrix multiplication in terms of multiplying a block of y by a block of z, along the lines of what we had seen in the previous slide, multiplying a block of y by a block of z. Now in order to do that multiplication of a block of y by a block of z, given that each of those blocks is made up of many elements, there will have to be three nested loops, just as we had before, an I loop, a j loop and a k loop, to do the individual element multiplications. But by structuring the matrix multiplication in this way, we are going to be able to get the benefit of reusing the elements of z, and therefore getting a much better overall spatial locality of reference, and therefore improved cache performance for the resulting program. This kind of an implementation, though it looks somewhat more complicated, may in fact end up being faster because of the benefits that it gets from improved spatial locality of reference, and would be well worth experimenting with. Okay, so it turns out that the matrix multiplication example was substantially more complicated than the earlier ones that we had seen, and hence our discussion of the matrix multiplication example did not go down to the level of calculating hits or misses, but was conducted at a level where we were analyzing the properties of the different elements that we see in the terms relating to the calculation that was happening within the loops of the matrix multiplication. Okay, now with this I'd like to wrap up our discussion of the different examples relating to doing cache calculations. I'll come back a little bit later to some closing comments on that. But before closing today's lecture, I wanted to refer to two questions which should come up at this point in time. Let me just remind you, up to this point in the course, we have understood a lot about the hardware, underlying hardware in a computer system. We've understood a lot about the underlying software in a computer system. And we have also understood something about how they relate to each other and how they could have an impact on the programs that we are trying to run on the computer system. And two of the important things that we saw along the way were that computer systems now must have cache memories. I motivated this from the perspective of the speed disparity between processors and memories, which is getting worse and worse thanks to various technology trends. And the other important idea that we saw was the idea of pipelining. The idea that the throughput with which instructions could be executed could be substantially improved rather than trying to make the amount of time that it takes to execute a single instruction as fast as possible. Right now, just to bring us up to some more recent developments in computer architecture, I wanted to talk about two questions to give some minor corrections to some of our perspective on some of these things. Okay, now the first relates to caches, and the question is, are caches really built to work on virtual addresses, or are they built to work on physical addresses? And let me just remind you what we mean by physical addresses and virtual addresses. You recall that the processor generates an address, and typically we understood that the addresses were virtual addresses and that the address had to undergo translation to generate an actual physical or main memory address. And this translation was done by a piece of hardware which we call the memory management unit. Okay, and it is the physical or main memory address which could actually make meaning as far as the hardware main memory is concerned. But we understood that this translation step did have to take place to translate a virtual address to a physical address. Now, when we talked about caches, I didn't actually indicate whether the cache was organized to take in a virtual address or to take in a physical address, which is why we'll actually refer to this in a little bit more detail before proceeding. So the question is, what's the relationship between the cache and the address translation? Does the address translation happen before the address goes to the cache, or does the address translation happen after the address has gone to the cache? Okay, now the picture which I just drew was telling you that the CPU generates a virtual address, whether it be the address of an instruction or the address of a piece of data. It is an address from the address space of a process and is therefore a virtual address. And the MMU, the piece of hardware that does the address translation, translates it into a real main memory address. So it is possible that people could build caches so that the cache takes in a physical address. In other words, the cache could be built so that it views the physical address in terms of its least significant bits, which are the block offset, its intermediate bits, which are the cache index, and the most significant bits, which are the cache tag. Alternatively, things could be set up so that the virtual address itself is what goes to the cache, and the cache hardware is built so that it views the virtual address in terms of least significant bits being the byte offset, intermediate bits being the index into the cache, and so on. So these are really two different alternatives as far as the design of a cache is concerned. Caches could be designed to work on physical addresses, or they could be designed to work on virtual addresses. These are two design options. Now, if the cache was designed to work on virtual addresses, then we should note that there is the danger that the virtual address that is currently being required by the processor might not be present in the cache. And if it is not present in the cache, then the cache will have to be loaded with that particular piece of data from main memory. But main memory is organized in terms of physical addresses, and therefore before the address can be sent to the main memory in the event of a cache miss, the address will have to be translated. Therefore the virtual address will have to go through the MMU to generate a physical address which can be sent to main memory. However, you should note that if the virtual address when it goes to the cache is a hit, then the cache can immediately provide the data and there is no need for the address translation to happen. Therefore, the second option that we look at over here is actually to be viewed with some favor, because it is an option where the address translation can be avoided when it is not necessary. If you think about the first option, the one on the top, the address translation happens regardless of what happens inside the cache, because the cache has been organized to work only on physical addresses. Now, if you think about our discussion of the cache hardware just takes in an address. It doesn't really use any knowledge about whether the address is physical or virtual. It just views the different bits of the address based on the properties of the cache. The number of bits used for the offset is decided based on the size of a cache block. The number of bits used for the index is decided based on the associativity, whether it's direct mapped or associative, as well as the number of the size of the cache and the size of the cache block. Therefore, it doesn't really make a whole lot of difference to the design of the cache, as far as we can see, between whether it takes in a physical address or a virtual address. Addresses are addresses and just have to be viewed in by looking at the appropriate bit field from the perspective of the cache hardware. But we do need to have some terminology now, otherwise I'll have to keep on referring to the first option, or the option on the top and the option on the bottom. And therefore, I'll actually refer to a cache which has been designed to work on physical addresses as a physical addressed cache, and a cache which has been designed to work on virtual addresses as a virtual addressed cache. And once again, let me repeat, both of these are design options. There could be processors that have physical address caches, and there could be processors that have virtual address caches. Okay, now the question is, which of these sounds like a more beneficial, or which of these sounds like a better idea? And I'm sorry for phrasing the question in this roundabout way, but that's essentially what we're trying to discuss next. Which would be a better idea from the performance side? A virtual address cache, in which the cache uses virtual addresses, or a physical address cache, in which the cache uses physical addresses. And let me put some of the pros, or the positive and negative points of each of these on the screen. Okay, now one benefit you can see of the physical address cache is that the amount of time for a hit is going to be higher. So this is a negative. Why do I say that the amount of time that it takes for a cache hit is going to be higher? Just go back to the diagram of the physical address cache. How much time does it take for the data to come back from a physical address cache to the processor? The answer is it's going to take as much time as it takes to access the cache, but in addition to that, it's going to take the amount of time that it takes to do the address translation. Therefore, the amount of time to get a piece of information out of the cache is going to be more than was the case for the virtual address cache in the event of a cache hit. Therefore, the hit time is going to be higher for the physical address cache than it is for the virtual address cache. And this is a negative. It's not a good thing, it's a bad thing. This is why I talked about which is less preferable. What are the different negatives associated with each of these? So there's one strong negative as far as physical address cache is concerned. What about the virtual address cache? Okay, now the thing to bear in mind about the virtual address cache is we're talking about a situation where the cache is organized in terms of virtual addresses. So the address which comes to the cache is a virtual address. Now one must bear in mind that the virtual address has different meanings depending on what the process is. I could have a virtual address which relates to process 0 and another virtual address which relates to process 1, and the bit patterns associated with the two virtual addresses might be exactly the same. Both of them could be hex A000, but we know quite well that hex A000 from the perspective of process 1 means something quite different from hex A00 from the perspective of process 0. Each process has its own virtual address space. So from the perspective of virtual address caches, we have to bear in mind that within that virtual address cache, you might have data and instructions of different processes in the cache at the same time, and it's quite possible that two of the things in the cache at the same time for process P0 and process P1 might have the same virtual address but might refer to different entities, because it is because of address translation that one process is protected from another process. What does this mean? This means that we can't really afford to have data or instructions from different processes in a virtual address cache at the same time. So one possibility is that when we switch from one process to another, which is what I call the context switch, we may have to empty the cache. So when process 0 was running, it's okay for the different virtual objects of process 0 to be present in the cache, but as soon as the operating system switches to process 1, suddenly all the data and instructions of process P0 which were inside the cache under the virtual addresses such as A000 and so on do not mean what they should from the perspective of process P1. And therefore one possibility is that the operating system might use instructions provided by the hardware to empty the cache, invalidate all of the entries inside the cache. If this is not done, conceivably process P1, when it starts executing, would access the instructions and data left there by process P0, and those are not the instructions and data that process P1 should be using. Okay, now alternatively, and we need an alternative because this is an extremely expensive option, Remember, the cache contains 32 kilobytes of information that has been accumulated as having been found to be necessary for the process in the near future. If all of it is suddenly thrown out of the cache, then the programs will suffer in performance. So the alternative might be to complicate the cache directories so that in addition to containing information about the tag associated with each cache block, we also contain information about which particular process that particular cache block relates to. So in addition to having information like tag information within each cache directory entry, also include process ID or process information. And in doing a lookup into the cache, check not only whether the tags match, but also check whether the process IDs match. Is the process ID of that particular cache block the same as that of the process which is currently running? And if they are not the same, then that should not be viewed as a hit, but should be viewed as a miss. That is the data belonging to some other process. Okay, now this is one negative as far as virtual address caches are concerned. One has to be very careful about handling data and instructions of different processes being in cache at the same time. Now another problem which could occur as far as virtual address caches are concerned is something called a synonym. And a synonym, as you know from other contexts, refers to two names for the same entity. So we talk about synonyms as being two words which mean the same thing, or two names for the same entity. Now in the context of virtual memory, one could talk about synonyms as being two virtual addresses that translate into the same physical address. And this could happen, for example, if I have two processes that have some shared data. You will recall that we talked about the idea of two processes, if they have to cooperate towards a common objective, they might be able to cooperate by actually having shared variables. And the operating system might provide support for that by allowing the mappings of the two virtual addresses of those two variables to be mapped into the same physical address. So this possibility does apparently help us in writing cooperating programs made up of many processes. But if one does have a situation where there could be two virtual addresses that translate into the same physical address, what does this mean from the perspective of a virtual address cache? It now means that the two different virtual addresses, maybe virtual address 0 and virtual address 1, which actually refer to the same piece of data because they have the same physical address, differ in their bit patterns, and therefore they would actually end up occupying different locations in a virtual address cache. What does that mean in terms of the data? It means that I could actually have two copies of the same piece of data inside a virtual address cache under its different names. And under one of the names I might modify that piece of data. And therefore I could have a situation where the shared variable has one value from the perspective of process P1 and another value from the perspective of process P2. And that's a dangerous situation to have and could arise whenever we have more than one copy of a block inside cache. So on all of these counts, it looks like having a virtual address cache may complicate the situation and not necessarily be a good idea. When we talked about virtual address cache in the previous slide, it looked like the virtual address cache was a clear winner over the physical address cache. Why? Because the physical address cache has a much longer hit time, and the virtual address cache has this benefit that you don't even have to do the address translation if it is a cache hit. So it looked like a clear choice, a clear beneficial choice. But when we looked into the mechanics of what has to happen behind the scenes, we understand that both of these have some negatives and that we do need to look into this a little bit further, which is what we'll do in the next lecture. In the next lecture, I'll actually go back and complete our discussion of these two questions. We'll close our discussion of question 1 by talking about what we might expect to see in the different caches of modern processors. We have still not fully understood whether we should expect to see physical address caches or virtual address caches, but we do understand now that there are these two possibilities and that the real processors that we deal with might be using either physical address caches or virtual address caches. And we will then come to the second question, where we'll talk a little bit more about what's happening in the pipelines of modern processors. So we will postpone both of these two topics to the next lecture. And I'll stop here for today. Thank you.